All right, so yeah, thanks for showing up. We're going to talk about private classical communication. Okay, and I'll figure out what we'll talk about for the last lecture later on. Okay, but we've been building up with various communication protocols. So what are all the communication protocols we've done? We've done quantum data compression. We've done entanglement-assisted classical communication. We've done classical communication. So what I'm hoping to do today is to do private communication. It'll also be such that we cannot go into all the details. And then next time, hopefully we'll talk about, I think we'll talk about quantum communication. So, but each of these communication tasks occupies like a whole chapter in the book, right? So entanglement-assisted communication, I believe that each of them are like almost 100-page chapters, right? And so we're really just giving you a taste of it. But if you're interested in diving in further, you should really read the chapters, because there's all kinds of details with proofs that we're skipping. We worked out things for examples of channels. There's a lot of thought that goes into these strong converse proofs. They're much harder to get than the usual converse. So anyway, encourage you to do that. So private communication, what is the setting? Again, we're going to think about the single shot, the one-shot setting where you have a single use of channel and develop everything there. So the diagram will look almost exactly like unassisted classical communication, with the exception that we will now think about the environment. Okay, so now what we will do is there will be a channel of interest. We will purify it, right? That's what we're doing here. There'll be an output that goes to Bob. There's an output that goes to the environment. So that's not available. The key point is that it's not available to Bob, right? And now in private communication, we want to explicitly think about the system, all right? Okay, so the goal of private communication is to send a message privately to Bob, such that only Bob can decode, and Eve, we will now personify the environment as someone named Eve, for eavesdropper. We do not want Eve to be able to figure out the message that's being transmitted. And we will have a specific criterion that determines performance of secrecy. Okay, so we'll have, in some sense, two criteria: reliability, that Bob can decode, and secrecy, that Eve cannot. And we should emphasize, so in order for a channel to have a strictly non-zero classical capacity or entanglement assisted capacity, it just needed to be different from the replacer channel. It needs to be different from a useless channel, right? So remember, in classical communication, the information quantity governing the rate at which you can communicate, let's say the entanglement assisted case is like this. Why don't we use rho? So the entanglement assisted case was like this. Where this is a replacer channel that traces out the A system and replaces it with a state signal. So, as long as the channel is not completely useless, then it has a capacity. Right? So that's kind of remarkable in and of itself, but at some point it becomes intuitive. Unassisted classical communication is when the R system is classical. Okay, and that ends up being the rate. Okay. So what's different here is we now have an extra criterion. We want Eve not to be able to decode. So not all channels will have a private capacitor. Okay. So if you work it out, this works out to this. Okay. So I'll just tell you what we'll find. So the sense of what we're looking for as we go along. We're going to be, what's going to come up in both the upper bounds and the lower bounds is a quantity called private information. Okay. So it's a quantity that's like this. It now becomes a difference of mutual informations. So the rate at which you can send messages privately will be this difference. This is the rate at which Bob can decode classical information. But if you want it to be secret, you have to pay this price. You have to cut off this amount of information to make sure that what you're sending to Bob is secure from Eve. So not every channel will be such that this quantity is strictly greater than 0, right? So how are you going to calculate this? Well, you take this quantity will be with respect to a state rho XBE, classical quantum state, tensor, an isometric extension. And then these classical states correlate, these quantum states correlated with the classical information over here. Okay. So not every channel will be such that Bob has an information advantage, right? So what's an example of a channel? Let's think about a family of channels, the erasure channels. Right? So the erasure channel, the qubit gets through with some probability, and with the complementary probability, it gets erased. It gets replaced by a state E that's orthogonal to every input state. Okay? So that's the original channel. And then what you can show, and it's kind of intuitive from the perspective that if you act with a unitary on a state, then the information doesn't get lost, right? It's like reversible. And so if this is the dilation, then if you trace over E, you get back the original channel. But if you trace over B, you get the complementary channel. So for an erasure channel, the complementary channel is just P flips, okay? And so it's consistent with what happens with unitary evolution in quantum mechanics. If the overall evolution is unitary, then the state cannot be lost. So what you see is that if with probability 1 minus P, the state's going to Bob in full, then that means that Eve, with that same probability, is getting the erasure state. Okay? And if the state is lost to Bob, such that it's getting replaced with this erasure state, well, overall, it's not lost. What is it doing? It's available to the environment. Okay, so that's the interpretation of it. So, if the probability of not being erased is greater than 1/2, that means that Bob has an information advantage. Bob has a higher chance of getting the inputs to the channel. Okay, so in that case, and so that's when P is less than 1/2, Bob has an information advantage, and this quantity will be greater than 0. Okay. It might depend on the ensemble you choose. If you take a maximum over all ensembles, then surely this will be greater than 0. Okay, but if P is greater than 1/2, then Eve has an information advantage, and the private information will simply be 0. If you optimize overall inputs, the private information will be 0. So there will be no private capacity if the ratio probability is greater than 10. And that's simply because Eve always has an information advantage. When P equals a half, the two channels are the same, right? That's when they're symmetric. And in that case, the private information is always equal to 0. Okay, so that's just some kind of intuition for this scenario, and the rate quantity we'll be looking for throughout the lecture. We're gonna have one-shot versions of this mutual information and this mutual information. This one will be close to what we had before, hypothesis testing mutual information, but this one will be something different. Okay. All right, so let's get going with it. And some things will, at the beginning, look a bit familiar, but we'll have this new criterion of privacy. Okay, so this, you can see it that it looks very similar to unassisted classical communication, but now there's this new thing. Okay, so let's write down some things. Initial state of the protocol. We'll call it phi P. So that's the same as before, and it's just, Alice is picking a message according to this distribution. EM makes a copy of it, and that's what she sends through the encoder, through the whole protocol. And so the value in this register is what she wants to keep private from E. Okay, so the final state of the protocol is what we'll call omega again. And that's going to be the initial state with the whole protocol acting on it. So not much different from the unassisted case. However, we'll have the isometric extension of the channel. Okay, then we do similar things that we had before. We'll define the encoder when it acts on these classical states. That produces quantum code words that are being sent through the channel. Now it will be important for these quantum code words to allow for mixed states. One thing we didn't talk about previously, probably should have, is that when you're sending classical data unassisted, it suffices to use pure state code words. Okay, there's no advantage to be had by using mixed state code words. Okay. And I believe the argument for that is just like a data processing inequality. Using data processing and the label information. Okay. So, but for privacy, it's actually essential to be able to use mixed states because there will be randomness. The key idea for coding is that there will be randomness in these code words that Alice uses to confuse Eve. Okay, so the mixedness will be essential. All right, the decoder. Similar to before, it's just a measurement channel with measurement operators. And then this right here is the probability to decode the messages M hat if the input state is tau B. Okay, so then we can write the final state. I made a typo here. Final state involves the E system. Final state omega involves the E system. That's now there. Right? I guess I was so used to writing in previous lectures without it. So using this and how we write the encoder, how we write the decoder, we can write the final state like this. M prime. There will be the initial distribution of the messages. There will be the probability to decode message M as M hat as before. But now there will be states of the environment that depend on M and M hat. Okay? These states we'll call omega M hat. And how are they defined? Well, let's define this distribution. Probability of decoding correctly. Or the probability of decoding M hat through the M was input. Like this. Similar to before, but now I'm writing the isometric extension. It doesn't really matter because in this trace, E gets traced over anyway, and you get back to the original channel. Right? So this is actually equal to the same expression we've been writing, or at least that we wrote the last time. Okay, but what are these conditional states? It's going to be when you send M's code word through, isometric extension acts, measure, Bob measures M hat on system B, but now you do a partial trace over system B. Okay? And that gives you a state, that gives you an operator on system B that depends on M hat and M. If you divide by this probability Q of M hat given M, then you get a state. Okay? Is that all right? So that you can do, you work with this equation here, you substitute definitions in, right? Put that there, and then one thing that might help to clarify the situation is when we wrote trace here, it might give you the impression it's a full trace, but you can think of it actually as a partial trace, right? So when you plug in one share, if you plug in the state tau BE and you do this channel, it's actually a partial trace. Okay, and there's some state that's left over in system A. That's the only thing that needs to be clarified. And then you kind of work through it and you see you'll get this. Okay, so that's the actual state of the protocol. What is the ideal state for secrecy? Okay, so why don't we think about that? The ideal state, well, we want M hat to be the same as M, right? That's so that Bob decodes correctly. And we want the eavesdropper to be able to learn nothing about M and M hat. So the eavesdropper state should actually have no dependence on M and M hat. That's the ideal state at the end of the protocol, such that we have reliability and secrecy. Okay, so the ideal state will look like this. So there exists, we'll call it sigma E, state of the eavesdropper, such that this is true. And this is the same as phi bar P M tensor sigma. So there you see it, you know, if this is the final state, then it's in tensor product. Your Eve system is in tensor product with M and M hat. And so, you know, Eve cannot learn anything about the message being sent. She might as well do random guessing, okay, of the message. And then she has a 1 over the number of messages chance of guessing, or sorry, it depends on the distribution, okay? It depends on the distribution, but let's imagine that it's a uniform distribution, then you'll have a 1/m chance of guessing the message. Question?
Yeah. I was not able to understand, like, before dumping E to the environment, why aren't we like applying a replacer channel?
Are you thinking of in like cryptographic terms?
Yeah.
Like where people talk about a simulator? This is the way we think about information theory. The justification given is what I said. Whether these two are equivalent, it's a good question. So in information theory, we allow for an arbitrary state of the eavesdropper. I believe that if we force this to be the marginal of, let's see. So if you have this state and you trace over M and M hat, you get a marginal state, right? And then if this is that marginal, then I think they're equivalent.
Yeah.
Oh, so you agree?
Yeah.
Okay.
This is for like this sigma is like a constant.
Mm-hmm.
So we can like use we can have a replacer channel which just replaces that state.
Mm-hmm.
Then I think the private capacity will be just the mutual information between X and B, and X and B replacing it. Because there is
X and Z. I know the private capacity is always formulated in terms of this mutual information difference.
Yeah, but the second term won't be zero because we're already like dumping. Yeah,
But it's something you do as like a simulator of an ideal protocol,
even
right?
if you have like a quantum channel, like any protocol, if you think about it, why can't we just at the end of the protocol before dumping E to the environment, why can't we just apply a replacer channel and the information won't go away? Because anyway, there is no cloning, so no one can tap into the channel and clone it. So just applying a replacer channel will do right.
I'm not sure how to answer your question right now. We should probably talk about it later. It's an interesting point. So, I mean, like, it's something that you're doing to think about the part. It's not something that can actually be done, right? We model this as an eavesdropper system to which Alice and Bob do not have access, right? So, I mean, the setup, I should probably draw the dotted lines, right? Like, everything over here is Alice, right? And then everything here is Bob, and everything here is Eve. That's the model.
But like whoever designed the channel, let's say, again, there are two subsystems.
We can't modify the channel. The channel's given.
No, not the channel. Like we can just add a replacer channel for the second subsystem.
To here?
Yeah. Before going into the.
But all right, I think we have to. I think we have to have a discussion at a later time because I'm not sure. I know that this is like a cryptographic theoretical computer science way of thinking about cryptographic protocols, but how I'm presenting it is how we think about it in information theory. Okay. All right, so, this is the ideal state. You can talk about two different criteria. One would be reliability. This is the same as before, that 1 minus Q of M given M is less than epsilon for all messages, right? To be able to decode reliably. That's what we had before for both entanglement assisted and unassisted. Secrecy is this. There exists a state sigma such that the fidelity between sigma and when the complementary channel acts on rho and A, that's greater than 1 minus epsilon. That should be true for all messages. Okay. So if this is true, it just means that, so what is the complementary channel, just to be clear? It's this map from A to E, right? So the code word row M is chosen, it's sent through this channel, and then you end up with, this state described here is this, is here in the diagram. Okay? And then if no matter what the message is, that's always close to a constant state, then Eve cannot figure out the message, up to some epsilon fidelity. Okay. So let's call this, I'll call it 1 and 2. And what we can do is capture the desire to have both requirements into a single criterion that's kind of related to this ideal state. So let's draw that. Okay, so the single error criterion is this, called P star error. You can beam them over states sigma E. Okay, so this is just that there should exist a state such that when you take the maximum error over all messages, it's less than epsilon. So okay, what is this P? That's the protocol, encoder, unitary decoder. Why don't I just write it here? This right here is what we call P. The protocol, taking as input, register M prime, you go into classical output M hat and E. So this whole thing is the protocol. And yeah, that's the single error criterion. And so there's ways to go between these, but if we have this holding, if we have this, okay, so then you can prove that 1 holds and 2 holds. Okay. So, yeah, you can just think of this as saying that there exists a state sigma E such that, well, let's translate this. So if this holds, then there exists a state sigma E such that this 1 minus fidelity, this whole thing is less than epsilon for all messages, right? So, and then it'll imply this 2. Okay, so it's helpful to have this one in order to get strong conversions. Okay, that's why we introduced it. It was easier to do so. Okay, so that's the setup. What is the one-shot private capacity? This has the same definition as we've had throughout, right? So the one-shot private capacity well, now we'll use the letter P for private capacity, function of epsilon, function of the channel. Same thing as before. Take a optimization over all message sets, encoders, decoders, such that the number of private bits you can send is as large as possible, subject to the constraint if this error criterion is less than epsilon. That's the one-shot private capacity. Okay. Any questions about the setup? Yeah.
A question about the secrecy condition.
Yeah.
So you want this E state to be correlated with the complement of the.
So in the actual protocol, the message is chosen, right? So call it little m that's in this register. When this encoder acts, it'll produce a state row m right here, right? And that gets sent through the channel. Bob will get n row m, but Eve will get nc row m. Okay, so the actual state that Eve gets at this point is this, all right, in the actual protocol. And what the secrecy criterion is saying is that we want all of those states to essentially be indistinguishable from some state of the eavesdropper. Yeah. You could ask me why didn't you use trace distance? It's a legitimate question. The reason is that the converses are cleaner with fidelity. So, but then I can't remember, maybe the achievability part will be cleaner with trace distance, but we just had to make a choice. I do personally think that trace distance is the better measure, but some of these debates are a bit silly. So, you know, we had those two operational interpretations in terms of absolute deviation of probabilities that could be observed, right? And then also in terms of hypothesis testing. And so those two like really kind of separated it, and I feel like the interpretation for fidelity is not as strong. So, okay, so let's leave that at that. So this is the main thing we're interested in. Actually, this one-shot private capacity, right? And so for the remainder of the lecture, we want to talk about upper bounds and lower bounds for this. And somehow we're not going as fast because I'm throwing that bit about private information, but I think that was important. So there's one bound I want to mention briefly, but I think we have to skip the details. The details are extremely interesting, and I encourage you to read the book. There's this notion of private state in quantum information, which I think Vishal knows about very well because his research project was using that. But it allows you to think about, I'll just say briefly something about it. So here we're thinking about a tripartite scenario. Alice, Bob, and Eve. Okay. In quantum information, what do we always do? We purify, right? We purify all the systems, and that's like give a global picture of everything. Right. So we could look at this. We could say, oh, here's a maximally classically correlated state. What's the purification of that? A GHZ state, right? A GHZ state is this. Superposition. If you trace over this one, you get the maximally classically correlated state that we erased, right? So you purify that, you get that. You can then purify Alice's encoder. We've already purified the channel. You can purify Bob's decoder. Okay. Then what you can do is you can go from the tripartite picture to a bipartite picture. Okay. Once you've purified everything, you can trace over Eve. You can change the goal to being of the protocol to generate something that's called a private state. Okay. And a special example of a private state is a maximum entangled state. Okay. And when you make this leap from the tripartite picture to the bipartite picture, you can use the tools of entanglement theory to get bounds on private capacity. And that's something very interesting. It's unique to quantum information. Because we don't have purification in the classical world, right? And so this idea was invented by the Horodesky family. There's 4 of them. And 2005 was the PRL. I think 2008 was the IEEE paper. And it led to a lot of insights in quantum information. So what I will say now is that using those ideas that we spoke about roughly, you can get an upper bound on the private capacity in terms of an entanglement measure, relative entropy of entanglement. Okay. This will be a one-shot measure. Okay, so we write this notation. It depends on epsilon. R is for relative entropy of E entanglement. It's a function of the channel. Okay, so, and it looks similar. Previously, we wrote the rate of a protocol as a comparison between the output of the channel and a useless state. For classical communication, it was the replacer channel. Now the useless state will be a separable state. Okay, so this is the relative entropy of entanglement for a channel. That's the quantity. Okay. So to get this, there's a whole theory behind it, but it's what I said. You purify everything, you trace out Eve, and then the goal is to make a private state, which is somehow very different from a separable state. Okay. So why is separable state kind of the right notion for privacy, for what's useless? Think about a separable state. You can write it like this. Lambda is a hidden variable in the background. Right? Sigma lambda S tensor sigma lambda B. So this classical information in a separable state can be copied, can be shared. And what purifies this? Remember, when we were talking about bipartite private states, we said you trace over E. But to get back to the purified picture, you'd have to consider the purification. What purifies a separable state? Actually, a separable state you can write as convex combination of pure states. So what purifies this is a state like this. Take the probabilities, the probability amplitudes. S lambda, B. And this lambda could be a classical register possessed by the eavesdropper. Right? That hidden variable, in principle, could be held by an eavesdropper. And if you have that hidden variable, then the state is just a product state. There's no correlations. There's no secrecy that can be generated. Like in private communication, you can use the channel to make a secret key. Okay? And it's like Eve has full information. So just with a separable state, it's useless for making a secret key. And there's a way to make all of this very rigorous. Okay. But this is one upper bound I at least wanted to state because it's a pretty important upper bound. Okay. There's another converse bound I want to talk about. See, this one right here doesn't look like the private information. Private information was the difference of mutual informations. Now I want to talk about a converse bound that looks like private information. Okay. So we're going to define what's called smooth max mutual information. Okay. This is kind of like on the different end of the spectrum from the hypothesis testing relative entropy. There's a sense in which, the Renyi entropies are, the Renyi relative entropies are ordered. There's a sense in which the hypothesis testing relative entropy is the smallest one, and the smooth max is the largest one. In fact, if epsilon is 0, then the hypothesis testing relative entropy is the smallest one. And what we're about to define, if epsilon is 0, smooth max will be the largest one. Okay. So smooth max, how do we define it? So it's a bipartite state we'll call rho AE. And we're again using this notation that's like mutual information. Okay. And there's a sense in which this will converge to mutual information if you plug in an IID state, normalize by the number of copies, and take the limit as the number of copies gets large. Okay. So what do? We do the smoothing procedure, where we look at states that are close to rho, right? So we call those rho tilde, so they're close in fidelity. We do that, and then also we optimize over the state and over states in the second form. And then we use the max relative entropy. Okay, so there's a fair amount of notation going on, right? But what you see is we have a relative entropy here, right? And again, with mutual information, you would recover mutual information by not smoothing and changing Dmax to relative entropy, right? Then you would get mutual information. And so this is, you can understand this as some kind of generalization of mutual information. And then we're plugging in these nearby states. So just to remind you, smooth max relative entropy is defined like this. It's the smallest lambda such that this operator inequality holds. Okay. It also can be understood as a limit of sandwich Renyi relative entropy as the alpha parameter goes to infinity. That's also, that holds, and that we showed in the book. All right, so what will our upper bound be? It'll be exactly like the private information that we wrote at the beginning. So it'll be the difference of Bob's mutual information and Eve's smooth max mutual information. And you optimize over all input ensembles. That's a one-shot balance. Okay. For a fixed ensemble, yeah, you can compute this as a semi-definite program, and this also, I believe, can be computed as a semi-definite program. But then when you subtract them, you optimize over input ensembles. It's hard to compute. Okay. All right, and what is the state rho that we're evaluating these information quantities for? It's this kind of state. Okay, so let's try to prove it. I think we have to eliminate this stuff. Sorry. Okay. So think about an actual protocol. Remember the reliability criterion, we've used it twice now, and we can use it again. The number of bits you can send is less than the hypothesis testing mutual information. This tau MBE. Uniform distribution over messages. Quantum code words being sent through. Isometric extension. Okay, so that we're just invoking directly again, right? This is now the third time we're invoking it. And it just, establishes a relationship between the number of bits, the error, and the information like quantity. Okay. So the key thing now is to incorporate this term that we're subtracting off for E. Okay. So from the privacy criterion, or we also call it secrecy criterion, what do we know, or what can we infer? That the fidelity of the actual state with this tensor product state is greater than 1 minus epsilon. There exists a state sigma E such that this is true, right? So it's like this is the actual state from the message register and Eve's register, and then it's very close in fidelity to a tensor product state. Okay. So now what we can show is this implies that, and I think this is along the lines of what you were thinking earlier, we can show that the smooth max mutual information of this particular state this particular state is less than 0. Now you were saying like equal to 0, right? So I think I understand now what you were saying at that point. This is indeed true. If you look at the, or it's very close to 0, right? I think you wanted to look at the mutual information between the actual message register and a protocol in Eve's register and deduce it 0. You're right, yeah. And that's what we're using here. But the point I was making is that when you then look at the private information optimized over all possible input ensembles, that doesn't necessarily have to be the case. Like over here, it could be that this is strictly non-negative for some choice of ensemble. And overall, it would do better than the case when this is 0 if this quantity is actually larger, right? So that's the point. And so we're encountering that right now. So yeah, you're on top of that. Okay. So to arrive at this conclusion from this statement here, there's a lot of symbols going on, but we can just use this definition, right? This involves an infimum over nearby states, an infimum over these states here. Maybe I should call it different letter. I don't know, zeta, so we don't confuse the times. Just some other. Sorry, It's C. So we have an optimization, two optimizations, right? So if we want to get this upper bound of 0, we can just make a choice of rho tilde and C, right? So what should we choose the tau tilde ME to be? Let's just choose it to be tau M tensor sigma E. Why can we do that? Well, it meets the fidelity criteria. Right? Fidelity criteria for the smoothest has to be larger than 1 minus epsilon. Right? So we choose it to be that, and then we can also choose this CE to be sigma E. Right? So then this implies that since smooth max involves an infimum over all such states, then we'll get that this one is less than D max. You just plug it in the definition, right? D max tau tilde MB to tau tilde M tensor E. Tau tilde M is the marginal of this state with respect to tracing over E. So we just plug in, you'll get D max tau M tensor sigma E tau M tensor sigma Z E. Now the states that are the arguments to the relative entropy are the same, and that's 0. So that's the argument. It might seem like kind of a trivial argument, but that's the argument. So we get this bound. We could question how good this bound is. I mean, why is it good? Well, it leads to the right thing asymptotically, or at least what we think is the right thing. For some channels, it leads to the right thing. In general, we don't have a formula for the asymptotic private capacity, just like we don't have a good formula for the asymptotic classical capacity. We have to use the regularization. So anyway, let's finish off the proof. Let's finish off the proof. Okay, so what we showed is that this quantity is less than 0. So that means that, well, this is going to be less than minus, we can just subtract it off, right? Now we have this quantity, oh, E, sorry. Okay. What's the next step to get the upper bound? Exactly. That's right. So the reasoning was similar as before. To get this upper bound, we used an upper bound in terms of mutual information between M and M hat, and then we used data processing to get to this. That's what we did in the past, and we're using it again. Okay, and then now we subtracted, or like we added in this other quantity. At this point, the bound still depends on the probability distribution over the messages and the encoder. And then we want it to depend only on the channel. And so if we optimize over all possible encodings, then we get this upper bound. Okay. So that's that upper bound. We have about 20 minutes left. We'll see what we can do. I want to try this lower bound. I want to at least give you the main sense of it. Okay. Any questions about the upper bound before we move on? There was a final step where we optimize over encodings, then we get this quantity, and then that's the whole proof. All right. Okay. So let's talk about the lower bound. And this is where I think you see something very interesting. Usually with the achievability proofs, there's some kind of clever idea that someone came up with, right? Like for entanglement assisted coding, it was position-based coding, which is this clever coding idea, right? For unassisted, it was that we took that and we allowed for shared randomness beforehand, and then we de-randomized. Now there will be a new idea, and that goes back to the 70s from someone named Aaron Weiner. Okay, so the lower bounds. The idea will be, again, use position-based coding. Now, in conjunction with a technique called convex splitting. This is a technique that maybe you know. Rahul Jain
Yeah.
came up with it with Anurag Anshu. Yeah, and you were working with them in Singapore, right? Yeah. Okay, so have you seen it presented before? Or? No. Okay. I want to just show you an example of the coding scheme, because the coding scheme is so simple that it's nice to at least see that. Like we have about 20 minutes. I want to try to respect the time. So let me skip some of the discussion of convex split and we'll return to it if we have time. But this will be the idea. So there will be a message variable M. It takes values 1 through M. Big M will be the number of messages you can send. All right. And we don't confuse that with the message register. But in addition to a message variable, so this is labeled message variable. There will be a randomness variable. Okay. Local randomness. Okay. And we're going to assume that Alice, Bob, and Eve share public randomness. Okay, so the last time we described that somewhat in a silly way is looking at the sun. Now they all look at the sun. They see the same value with some probability. Alice, Bob, and Eve share this, call it rho x, x prime, x double prime. So there's some distribution we'll call P of x. Okay. So that's a state, right? That's a public randomness state. Each value takes a there's this probability distribution describing how each value is generated, and then once it's generated, each of them gets a copy. Okay. So we allow them MR copies of this. Right. So that's the state they'll share. It's a lot of randomness. And again, we're using this as just like a proof tool. eventually at the end, you can de-randomize the protocol. And there's a whole like thing about how to do that. I actually wrote a whole paper about doing that. After they came up with the position-based coding convex split, then I wrote a paper on which this chapter is based. Okay. And we won't get into all those details of de-randomization because it's too much. But we can imagine the state is looking like this. So give me some time. Maybe 9 of them, just to, I think it's helpful to illustrate the part. Okay, so this we'll call x11, x prime 11, x prime 11. Maybe I'll make some abbreviations. We'll call x bar, x underscore this, right? So then I won't write all the labels in every single line. Okay, so this is the case when M is 3 and big M is 3 and big R is 3. Okay, so this is an example. So only 3 messages to send and 3 randomness choices to try to confuse Eve as to which message is being chosen. Okay, so the way it will work is that, if Alice wants to send message M, that corresponds to choosing a column. Okay, so we're going to call these variables little mr. The first index is little m, the second index is little r, right? So if Alice wants to send message M, that corresponds to the choice of a column. Okay, and so then fix R at random. So when I say at random, I mean uniformly at random. Okay, so as an example, suppose M is 2, right? That corresponds to the second column. And then she'll pick the little r at random, and then suppose that it comes out that little r is equal to 3. Then what will she do? Her share of the randomness is, remember, all the top lines are Alice's shares, the middle lines are Bob's shares, and the bottom lines of each are Eve's shares of the randomness. Okay. So then what will she do? She'll take this system, send it through an encoder and a channel. Then we have to think about the isometric extension. U. Okay, so the encoder just produces a state relative. And then this is sent through the channel with isometric extension. It leads to a state for Bob and Eve. Okay, so how will it work? Well, Bob wants to know the message. Okay, and what he will do is he'll decode not only the message but also the randomness variable. Okay, and so that just involves Bob doing position-based coding. Okay? He'll do a check here and here. Product state, no. right? Same idea behind position-based coding. I check here and here, product state, no. Here and here, product state, no. No, no, boom, now there's correlation. Right, and so that's how the position-based coding will work, just like before. So Bob decodes M and R using position-based coding, PBC. But that's not anything bad. Okay, so with the position-based coding, both, these are, I don't know if there's a name that captures both. The sequential aspect is the fact that you're using the sequential tests in the quantum union bounds. In the original paper, they formed the square root measurement, which is a different way of decoding, which is a little more difficult to imagine how you implement it physically. Okay, using position-based coding, what do we know? We know from before that as long as, so Bob is trying to code both the message and R, right? Both little m and a little r. So if we know the total size of the set, the log of number of bits, is the hypothesis testing mutual information. The row minus the direction term. Then Bob can decode reliably with epsilon error probability. Okay. So now, what is the new aspect? We have to think about Eve's reduced state for a fixed value of the message, but a uniform choice of the randomness. Okay, so let's write that down. What do we? I think we can all write this down. All right, so for a fixed value of M, what is the reduced state of E? Right? So for this diagram, it's going to be all of the bottom wires. Right? Eve has all the bottom wires with these shared randomness states, and this E system here. And R is chosen uniform at random. Okay, so the state will be mixed over the choice of R. All right, so that will be this. Eve has the double prime systems. This state right here is this one, the top and bottom line. This diagram is for a fixed choice of R as well, right? If R is random, then the state is equally this state, the one where this is over here, and the one where this is over here. Okay? Because remember, the randomness, like the coding scheme involves Alice choosing a message, that's choosing a column, and then she's randomly picking R to figure out which X to send through. So it's going to be, it's like a slot machine with 1 over big R probability, it's one of these. And in this example, we just said it was this. Okay. So, but it could be a mixture of this, this, and this. And so that's the thing. If the column size is very large, it can be very hard to figure out. It makes it hard to figure out which choice was made. Okay. It's like a needle in a haystack. So let's finish this off. The reduced state is this. Okay. So the sum corresponds to, the averaging over, was it this one that was sent through, this one that was sent through, or this one that was sent through. Okay, that's the state. And so the claim is that as R gets larger, it becomes more difficult to distinguish this state. Give it a name. Yeah, call it row M. From a product state. Looks like this. It's all of them except this is now in tensor product. Row x11 tensor where this is now the marginal in system E if we traced over these two. Okay. So that's the claim. And the question now is to quantify the trade-off. Like, how large do we need to make R such that this state is epsilon distinguishable from this state? Okay. Because this state now is a constant state independent of the message. That's what we wanted for a private communication code. Right? This state here depends on the message because it depends on the column that you chose. Right? The message corresponds to the column that you chose. And so randomly, this is here, here, and here. Okay, so that's the basic idea. And I want to give you a sense of why we can choose R to be a certain size. Okay, so let me state the claim. So this is the convex split lemma. What does it say? Log R is greater than a variance of smooth max mutual information and you need a little wiggle room such that you have this extra added and constant, like R has to be sufficiently large now, so the error term that you add in is additive rather than subtractive. So if this holds, there exists a state rho tilde E such that fidelity between this actual state and the desired product state. So is larger than 1 minus epsilon squared. And then there's also a guarantee about this thing. I think this is correct. The rho e, the fidelity between rho e and rho tilde is greater than 1 minus epsilon, something like that. Is that right? It might be epsilon minus. That needs to double check. I think that's correct. I think it is true. Sorry, it's not that important, right? Like, okay, but that's the claim of this convex split lemma. Okay. But the basic idea is that as this gets larger, it gets harder and harder to figure out where there's a correlation, right? Like, all right. There's something else I wanted to- I had an intuition for this convex split. Okay, I want to try to give you some intuition for why this holds, just some basic intuition. All right, what is the intuition? Well, let's forget about the smoothing parameter and just think about how max mutual information is defined. All right, so we'll let lambda star equal the max relative entropy between rho xt and rho x tensor rho. Right, so what does this mean? It implies that rho xt is less than 2 lambda star the tensor product star. So suppose that you are restricting your ability. If you're trying to distinguish this state from this one, you'll allow for all possible measurements on all the systems, right? But suppose you restrict your ability to distinguish them between one of the x's and the E system, right? Between just one of the x's and the E system. So it's like the only measurements you're allowed to do are here, here, and here. Kind of like the way that Bob did position-based coding, right? Okay, so if you restrict your ability to that, then we have to figure out what is the reduced state for a single one of the X systems and the E system, right? So suppose we pick the X to be the single X system to be X11. Without loss of generality, we could do that because of all the permutation symmetry, right? So let's look at the reduced state of X11 and E. Okay, so what is that state? Well, and actually, let's just focus on a single column. Let's do that also. We're going to focus on a single column. Okay. So in a single column, there are big R systems. Right? Here, R was three. So there's three copies. Right? So we're looking at the reduced state of. So it's actually X, M, and 1. All right. Where the column corresponds to the message and the first one there. So we're looking at the reduced state of here and here, right? Well, we said that the overall state would be a mixture of when the encoder acts here, or when it acts here, or when it acts here. Right? So most of the time, it's just acting on one of them. Sorry. For most of the terms in the sum, the encoder is not acting on the system. So the point is that the reduced state will be 1 over big R, a correlated state, rho xe, plus 1 minus 1 over big R, the product state. Okay. Right, because why don't we write it down for this example, what the overall state is? I think that would be helpful. So overall, for this example, the state will be 1/3 rho x to 1 tensor rho e. Plus rho x and then the products, and then the correlates. Right? That's if we're looking at this system and this system of the 3 different possibilities, where the encoder acted here, or one possibility. That will actually be this term. The other possibility is when the encoder acted here, and then that will correspond to this term, and then when the encoder acted here, that will correspond to this term. Yeah.
Should it be X22?
We were looking at the reduced state of this system in E when there's one of three random things that happens. Either the encoder acts here, here, or here. So remember, the way the code works is that a message is chosen that corresponds to fixing a column, and then randomly R is chosen. So randomly, a row is chosen.
So don't we need to look at every row?
What I wanted to make to give some kind of intuition behind how this is working is restrict what Eve can do to distinguish this state from this one. So have her just look at 2 systems, system E and this system. Okay. So if we do that, then this is the reduced state. But the point is that in this reduced state, there's a very low chance that the state is the correlated state. Okay. And so the basic idea from here is, well, roughly using this, you can replace this rho xe with the product state up to this factor, okay, to the lambda star over R, rho x tensor rho e, plus this term here, the same product state. That's a bit small. And then when you rewrite it, you'll get 2 to the lambda star. Sorry, you get 1 plus 2 to the lambda star minus 1 over r, and then this product state. Okay. Then if you choose this 2 to the lambda star to be approximately r, then this normalization factor is the same as that for a state. Okay, and so it's roughly that when this upper bound is like a state, then this state is becoming very similar to this upper bound state. Okay, that's a bit vague, but that's kind of the basic idea. I wasn't sure how else to explain the proof because the proof is a bit complicated. Okay, and with limited time. But the point is that that's what gets reflected here. You know, if we choose 2 to the lambda star to be approximately r, that's the same as log lambda star equal to log r. What is log lambda star? That's this max relative entropy. And so that's what's appearing here. Like as long as this log r is chosen sufficiently large, then this state on 2 of the systems will look like a product state. And then Eve will not be able to distinguish to figure out where the correlations are. Okay. Yeah, there might be a simpler proof of the convex split lemma. I don't know. There are at least 2 different proofs that exist. There's the one from the original paper, and there was one that Andreas Winter and Ziwen Liu came up with that we put in the book. Okay, but we're quite a bit over time. So let me just make a final statement about the code and rate. So ultimately, we want to get a lower bound on log m, right? The number of bits you can transmit. So this we can write as log mr minus log r, right? This is what Bob can decode. We said Bob would decode both the message and the randomness variable. We said that as long as this was this hypothesis testing mutual information, then it could do so. We had to throw in epsilon minus eta, blah, blah, blah. Then log r, that's where we're choosing to be this smooth max relative entropy, smooth max mutual information. And that has to be this way. And then there are the correction terms, plus log, epsilon, et cetera. Right, and so what you get is that, again, we see this private information difference, right? And so this is a guarantee that as long as the number of messages is equal to this amount, then this coding scheme can be used, right? Alice randomly, given a choice of message, she picks a random entry from a column, sends over the channel. Bob will be able to decode. This guarantees that Eve will not be able to, right? Because for a fixed message, all the coded states will look the same. And so you meet both the reliability and secrecy. Okay, and then what we left to be done was the de-randomization and the expurgation. Okay, that's what we did last time for unassisted. And that's a pretty involved analysis. But we can just leave it at that. All right, so let's stop there. If you have questions, you're welcome to ask them. The convex split technique is extremely powerful. This has been used now in a variety of different topics in quantum information and resource theories. It's been used in resource theory of entanglement, thermodynamics, all kinds of stuff. It's very powerful because, it's a way of like erasing correlations. Right? Like you have the state that's correlated, and you want someone not to figure out that it's correlated. Well, if you embed it in all these other states and then do a random permutation, you get this state, and then the correlations are lost. Right? So it's also been used in understanding the thermodynamics of erasure. Yeah.
It's like throwing a state, your correlated state into the environment. Figuring out and it will eventually become a mixed state, like maximum mixed state. Because there are so.
I don't know if you can say it's a maximum mixed state. Maybe with a certain representation, it would be maximum mixed. Yeah, but indeed, it's a hell of a mix. You can say that. All right. Okay, so we will meet on Monday, and then the final presentations, we have to do them on Zoom. I'm sorry about that. Yeah. All right, so.